Hi everyone. Today we're going to be completing our notes on removable discontinuities and oblique asymptotes for rational functions. I want to start just by defining what is a removable discontinuity or a hole. A removable discontinuity is a hole in the function marking a point where the function is undefined. Removable discontinuities occur when you have a repeated factor that cancels out. So similar to vertical asymptotes, at x equals where these holes are, or these removable discontinuities, the function is undefined. Okay, so where vertical asymptotes are infinite discontinuities, removable discontinuities or holes are just those single points where they're undefined. This occurs when we have a repeated factor in both the numerator and denominator that cancels out. So let's take a look at example 1. Here we have f of x equals the quantity x minus 1 divided by the quantity x squared minus 1. I notice that the denominator can be factored to the quantity x plus 1 times the quantity x minus 1. And so what we get here is we have a repeated factor of x minus 1 in both the numerator and denominator. We can cancel out this factor. This reduces the function to 1 over x plus 1. Okay, so the graph of this function is going to look really similar to that of 1 over x plus 1. But we've got that removable discontinuity, and that happens from that canceled out factor. Let's start just by describing the end behavior. So I notice that this function, looking at the dominant terms, dominant term in the numerator is 1, and dominant term in the denominator is x. You could also actually look at the original function, x over x squared, which reduces to 1 over x, and this is going to approach 0. So that tells us that the limit of f of x as x approaches negative infinity is equal to 0, and the limit of f of x as x approaches positive infinity is also equal to 0. Therefore, the end behavior asymptote is y equals 0. Now let's talk discontinuities. So this includes both the infinite discontinuities, vertical asymptotes, and removable discontinuities, holes. So we'll start with vertical asymptotes. We've got one vertical asymptote at x equals negative 1, and that's defined by that factor x plus 1 in the denominator. So the equation for the vertical asymptote, x equals negative 1. We also have a removable discontinuity, and that happens from that factor that was canceled out, x minus 1. We find this x value by setting that factor equal to 0. So where we have the factor x minus 1, we're going to set that equal to 0 and get a value for x, which we can then plug in to find the y value of this removable discontinuity. So we're going to take x equals 1 and we're going to plug it into the reduced function here. So after we've canceled out that term, we're going to plug it in here into the reduced function. The reason why is because if we were to plug it into the original, we would get that it's undefined. We'd get divided by 0 here. So after we cancel out, we've removed that factor that causes it to be undefined, and then we can evaluate where the function would be defined if we didn't have that canceled factor. Okay, so plugging in 1 here, we have 1 over 1 plus 1, which is 1/2. So the coordinates for this hole, or the removable discontinuity, is 1 comma 1/2. All right, and we'll see what that looks like on the graph. Intercepts, so this is, we'll start with x-intercept. The x-intercept is where the numerator is equal to 0. Well, the numerator is just 1, right? So it's never going to be equal to 0. Therefore, we have no x-intercepts. For the y-intercept, we can just simply evaluate the function for f of 0. Okay, I'm going to plug it into the original function. So we have 0 minus 1 all over 0 squared plus 1. I'm sorry, minus 1. And when we evaluate here, we get 0 minus 1 in the numerator is negative 1 over 0 squared minus 1 is negative 1. We get 1 over 1, sorry, negative 1 over negative 1, which is 1. So we have the y-intercept of 0, 1. And then our sign chart. For the sign chart, we do not plot the removable discontinuity. So do not plot removable discontinuities on the sign chart. Okay, we're just going to plot, same as before, vertical asymptotes and x-intercepts. In this case, we only have one vertical asymptote, so one value on our sign chart at negative 1. if we look at the end behavior asymptote, we can see that it's y equals 0. So we can't consider the end behavior asymptote when creating our sign chart. So then we have to look at the y-intercept. The y-intercept at x equals 0 is a positive quantity, and I know that's going to be on the right-hand side of my sign chart. So we have positive. The multiplicity of the factor x plus 1 is 1, so that tells us that it's going to flip sign. Okay? So when we graph this, we know that we have a vertical asymptote at x equals -1. So let's go ahead and plot that first. We also have an end behavior asymptote, y equals 0, the x-axis. Okay? Now let's go ahead and plot our y-intercept as well, is 0, 1. And then we've also got a removable discontinuity at 1, 1/2. And I'm going to draw that as a hole in the graph. That would be like an open circle or a point that's not filled in. Okay? Now, using our sign chart to the left of -1, we see that the function is entirely negative. So I'm going to sketch this curve approaching the end behavior asymptote and approaching that vertical asymptote, staying in quadrant 3, so staying completely negative for that interval. On the right-hand side, to the right of -1, it's entirely positive. So approaching the vertical asymptote, we're going to be going up to infinity, and then approaching the end behavior asymptote, we're getting closer to 0. Okay? So we can see that this function, if you were to graph 1 over x plus 1, remember this is the parent function for the rational functions that's shifted to the left 1. So notice we've got that behavior here. This looks like our parent function. We're shifted to the left 1. But then we also have that removable discontinuity at 1, 1/2. So that's the only difference between these two graphs, is that hole in the graph. All right? Let's try another. Example 2, sketch a graph of the function f of x and state the following information. Well, first thing I noticed about f of x is that it can be factored. So I noticed that the numerator, there's a common factor of 3, so we'll go ahead and factor that out. 3 times the quantity x squared minus x minus 2, and that's all over the quantity x minus 2. Notice that that quadratic trinomial can be factored further, and so we're left with 3 times the quantity x minus 2 times the quantity x plus 1, and that's all over the quantity x minus 2. We've got a common factor of x minus 2, and so when we cancel those out, we're left with 3 times the quantity x plus 1, which if we were to distribute that gives us 3x plus 3. Using limits to describe end behavior, if we look at the original function or the reduced function, we see that the end behavior is going to approach that of 3x. So that tells us that the limit of f of x as x approaches -infinity is -infinity, and the limit of f of x as x approaches positive infinity is positive infinity. Because we're approaching -infinity and positive infinity, this does not have an end behavior asymptote in this case. For discontinuities, we'll start with vertical asymptote. That's where the denominator equals 0. Well, we don't have a denominator, it's just 1. So therefore, there are no vertical asymptotes. Removable discontinuity, we set that factor that we canceled out equal to 0. So x minus 2 equals 0, x equals 2. We then take that x equals 2 and plug it into the reduced function here, the reduced equation. So 3 times 2 and then plus 3 gives us 6 plus 3, or 9. So the coordinates for our removable discontinuity is 2, 9. Intercepts, we'll start with x-intercept. So x-intercept is where the numerator is equal to 0. So we have 3x plus 3 equals 0. Subtracting 3 and dividing both sides by 3, we get, 3x equals -3, so then x equals -1. So as an ordered pair, -1, 0 is our x-intercept. And then our y-intercept is when we plug in 0 in for x. And I'm going to do that into the reduced equation. So 3 times 0 plus 3 is just simply 3. So our y-intercept is 0, 3. Our sign chart, again, we plug in our x-intercept and our vertical asymptotes. We only have an x-intercept at -1. So then we look at our end behavior asymptote. Right-hand side's approaching infinity, left-hand side's approaching -infinity. And finally, our graph. We don't have any vertical asymptotes. We've got an x-intercept of -1, 0, We've got a y-intercept of 3, 0. And we've got a hole at 2, 9. And so we've got a hole all the way up here. If we were to sketch this graph, you might notice something about the graph. It just looks like the linear equation y equals 3x plus 3. And you'd be right. This is exactly like y equals 3x plus 3, but we just have that hole at 2, 9. Okay? Now I want to talk about oblique or slant asymptotes. So given rational function r, which is the ratio of two polynomial functions, p of x and q of x, where the degree of the numerator is exactly one more than that of q, the denominator, by the division algorithm, we can express r as ax plus b with a remainder r of x, so this would be a remainder polynomial, over the divisor, where the degree of the remainder is one less than that of the divisor. Okay? Because that ratio of the remainder and divisor approaches 0 as x approaches positive or negative infinity, right? That's because the degree is one less. It's bottom heavy. And behavior is it's approaching y equals 0. As we grow really, really large in x in both the positive and negative direction, this quantity here is going to be pretty negligible. It's approaching 0. So therefore, the function is just simply going to approach ax plus b, the line y equals ax plus b, which we see as in slope-intercept form. Okay, so we've got a linear equation that the function approaches as we approach positive and negative infinity. This line that the function approaches is called an oblique asymptote or slant asymptote. Okay, so let's see what this looks like. We'll start with example 3. Here we have f of x. I'm going to again start by factoring this function here. So I notice that the numerator has a GCF of x, so this can be factored into x times a quantity x plus 2, and that's all over x minus 1. Okay. First thing I notice is that the degree of the numerator here is 1 greater than the degree of the denominator, so that is a good indicator for me that this has an oblique asymptote. Okay. This function is approaching x squared over x, which approaches just simply x. Okay. So that tells us that the limit of f of x as x approaches negative infinity is negative infinity, and the limit of f of x as x approaches positive infinity is positive infinity. The equation for the end behavior asymptote is going to be that oblique asymptote. And the way that we find that is that we just go ahead and divide the denominator into the numerator. Okay, so we have 1. We're going to use synthetic division. So x equals 1, dividing into our quadratic binomial here. So we have 1, 2, and then 0 for the constant term. All right, so using synthetic division, bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. And then 0 plus 3 is 3. Okay, so our remainder here is 3. So what we get as a quotient here is we get x plus 3 and then plus 3 over the quantity x minus 1. And so what we're saying here is as x approaches positive or negative infinity, this third term here, the 3 over x minus 1, approaches 0, and it becomes negligible. So the function is going to approach the line y equals x plus 3. So the equation for the end behavior asymptote is the slant asymptote or oblique asymptote, y equals x plus 3. Okay. Vertical asymptotes, we'll start with where the denominator equals 0. We have at x equals 1. We don't have any removable discontinuities because we didn't have any canceled factors. Intercepts, we'll start with x-intercept. So that's where the numerator equals 0. We've got x times a quantity, x plus 2 equals 0. So that tells us x equals 0 and x plus 2 equals 0, or x equals negative 2. So we've got two, let me write those as ordered pairs. So we've got 0, 0, and we've got negative 2, 0 as our x-intercepts. For our y-intercept, I already noticed that we have an x-intercept of the origin, so that tells me my y-intercept is also the origin. But let's go ahead and evaluate just for good practice. So we have 0 squared plus 2 times 0. This is the original function over 0 minus 1. We get 0 plus 0 over negative 1 0 over negative 1 is 0. So here is our y-intercept 0, 0. Our sign chart, we've got three values here. We've got negative 2, we've got 0, and we've got 1. Okay? I know that the right-hand end behavior is approaching positive infinity, left hand is approaching negative infinity, and I know that the multiplicity of each of these factors is 1. So the one at 0, the one at negative 2, and the one at positive 1 are all 1, so it's going to flip sign over each of those. Let's go ahead and graph this. So we'll start with our vertical asymptote at x equals 1. We've got our x and y intercept of the origin, and we've got another one at negative 2, 0. And then we've also got our oblique asymptote of y equals x plus 3. So if I were to graph that, I know that y equals x plus 3 has a y-intercept of 3 and an x-intercept of negative 3 and a slope of 1. So I'm going to draw this as a dotted line. We can see that this is the oblique asymptote y equals x plus 3. Okay? Using our sign chart, we know that the function is negative from negative infinity to negative 2. And so we're below the x-axis here, and we're approaching this asymptote. So draw it getting really close to this line. Don't cross it. Get as close as you can. It then passes through that 0, comes up, goes back down and hits the 0 at the origin, and then returns negative and follows the vertical asymptote down to negative infinity. On the right-hand side of x equals 1, we have that the function is entirely positive. So it's going to be coming down from positive infinity, and then returning back up and following that oblique asymptote. So we've got this shape here. Let's try one more. Okay, so example 4, here we have f of x. Again, first thing I notice is that this can be factored. So factoring the numerator, we get the quantity x minus 5 times the quantity x plus 1. And that's all over x minus 3. Okay, so using limits to describe end behavior, I know this function is going to be approaching that of x squared over x, which reduces to just simply x. So therefore, the limit of f of x as x approaches negative infinity is equal to negative infinity. And then the limit of f of x as x approaches positive infinity is positive infinity. The equation for the end behavior asymptote, well, we've got the degree of the numerator is exactly 1 greater than the degree of the denominator. So let's go ahead and use synthetic division. Because we're dividing by a binomial, we have the factor x equals 3. Or the factor x minus 3, the root x equals 3. The quadratic trinomial, we have coefficients 1, negative 4, negative 5. Bring down the 1. 1 times 3 is 3. Negative 4 plus 3 is negative 1. 3 times negative 1 is negative 3. Negative 5 times plus negative 3 is negative 8. And so what we get is the linear binomial x minus 1, and then minus the remainder 8 over x minus 3. And again, that remainder, as we move way out to the right and to the left of the graph, this term becomes pretty negligible. It approaches 0. So the equation of our end behavior asymptote is the oblique asymptote y equals x minus 1. Discontinuities, vertical asymptotes we'll start with, where the denominator equals 0. So that's going to be x equals 3. We don't have any removable discontinuities because we don't have any canceled factors. Intercepts, x-intercept, where the numerator equals 0. So we have x minus 5 and x plus 1 equals 0. So then we have x is equal to 5 and x is equal to negative 1. And so as ordered pairs, we have 5, 0 and negative 1, 0. For y-intercept, we're going to evaluate the function f of 0. So I'm going to plug it into the original function. We get 0 squared minus 4 times 0, and then minus 5 all over 0 minus 3. Well, this is equal to negative 5 over negative 3, or positive 5/3. So as an ordered pair, we have 0, positive 5/3. One thing I noticed too, just like in polynomials, when they're written in standard form, remember that constant term is the y-intercept. For rational functions, where the numerator and denominator are also written in standard form, it's just the ratio of those constant terms. So -5 over -3. We can kind of see it from the original function. All right, so sign chart. We've got 3 values that we're going to plot, our vertical asymptote and two of our intercepts. So we have -1, we have 3, and we have 5. I know that the right-hand side is approaching infinity, left-hand side is approaching -infinity, and just like the last one, all of our factors have multiplicity 1, so the sign is going to change over each of these x values. Let's go ahead and graph. So we'll start with our vertical asymptote at x equals 3. We've got an x-intercept at -1. We've got another one at x equals 5. We've got our y-intercept of 5/3. So 5/3 is about 2 2/3, or 1 2/3. So that's right about here. And then we've got our oblique asymptote, which is y equals x minus 1. So I know that that has a y-intercept of -1 and a slope of 1. And so that looks like this here. Left-hand side, I know that from -infinity to -1, the function is negative. We're approaching that oblique asymptote. We're going to come up to the positive and pass through our y-intercept, and then approach infinity, approaching our vertical asymptote. On the right-hand side of 3, we are negative all the way up to x equals 5. Again, approaching that vertical asymptote. And then after 5, we're positive, and then approaching that oblique asymptote. Okay. So hopefully your graph looks a little bit better than mine. It's a little tricky to draw. Okay, try to get those nice and curved, because this is a rational function. They've kind of got like a little bit of a curve to them. All right. So these have been our notes on removable discontinuities and oblique asymptotes. We're going to get a lot of practice in class, so we'll see you tomorrow. Goodbye, everyone.